Okay, welcome back. Our next speaker is Markus Jungbluth. He is a solution architect at Santaro, and he will share his experiences on merging different service provider networks with a focus on MPLS and IP networks. Thank you.
All right. Yeah, welcome to my talk, Merging Service Provider Networks. My name is Markus, and as you can see, there's one other name here, Bastian. We prepared this presentation together, and unfortunately, Bastian couldn't make it due to private reasons today, so I'll be presenting our work. All right, let's dive right into it. Merging service providers. So if you look at the past 15 years, we've seen many mergers or acquisitions of service providers in Germany. We have a few headlines here. And the reason why they do this is usually because they have a build and buy strategy. So they extend their network by purchasing other networks. And in many of these cases, both the acquiring and the acquired network have an IP MPLS network. And this is what this talk will focus on. And just a little disclaimer, we know that there are many other challenges besides the IP MPLS network, optical networks, and also social aspects of merging engineering teams. But this talk will just focus on the IP MPLS part. So before we dive into the technical topic, a quick look on why is it interesting for a service provider to merge to ISPs. So one aspect is an extended network footprint. So for example, if either one of the ISPs could not cover all of Germany, by merging the networks, you can suddenly cover a larger area and provide service to more customers. Another aspect can be that if you have a different customer portfolio, for example, one service provider focusing on residential and the other one on business, you can combine those portfolios and also generate more business there. And the third one, probably the most important one, is cost savings. So potentially by merging the networks, you can save on cost for resources or services, with a few examples listed here. All right. So let's take a look at the technical topic. So essentially, when you have the two IP MPLS networks, there's a million ways that you can merge them. And today we're going to talk about a selected few. And at the end of the day, if you're in this position, it's up to you. You need to decide and find the way that is right to get these networks together. And I'm putting this statement out there just to make it clear that I'm not telling you you should do it in that way. Ultimately, that's a decision that you need to make when you work on the network. We're just talking and sharing a bit about our experience with this topic. So let's jump to the first one, NNIs. NNIs are great, and this is what we see many times happening a couple of months after the business deal has gone through, that the two networks will, as a first step, establish an NNI. What is an NNI? Well, it's nothing fancy. It's just a layer 2 connection. You have a bunch of VLANs on it, sometimes single stack, sometimes dual stack, depends on what you want. And this gets up and running really fast. So if you have the requirement to provide end-to-end services for customers that are positioned in the two networks, you can basically use this approach to get rapid value, essentially. And the concept, and that's one of the bonuses for an NNI, is really well understood, both by engineers but also by IT systems, because it's very likely that the ISP already has an NNI set up to another service provider, so all the processes are probably already in place. So, as you can see here, it's all nice and clean, but if you operate this for quite some time, so on day 1 it looks like this, on day 237 it can look something like this. You will have multiple NNIs in multiple locations. You will have to monitor their capacity to make sure that all the customers that you're passing through them will have enough resources for the services that you put on there. And you can also have effects like increased latency or traffic tromboning. For example, if you have a customer in Munich with 2 sites and you interconnected 2 sites in Berlin, they will most likely not like it. So again, your mileage or experience with this might vary depending on the requirements that you have. An NNI can be an approach. But our experience is that over time, especially with larger networks, they will get hard to manage. Okay, approach number 2. This is also something that we've seen is inter-provider or inter-AS. And the general idea behind this is not new. Essentially, use external BGP between two autonomous systems to exchange routing information. And well, this is new, and you all know it because that's how the internet is built. The only difference for inter-provider setups is that instead of only INET unicast and INET 6 unicast address families, you can also pass service families over it. For example, INET VPN or INET 6 VPN. And this inter-provider or inter-AS setup comes in 3 flavors. We have option A, B, and C, and they're to be seen in ascending order of maturity and scalability, with option A being the worst and option C being the best in terms of scalability. However, if you look at option C, it comes at an increased complexity, which is also something to consider. So again, this can be a nice approach to generate rapid value if you want to merge two networks. It is, at least from my experience, more or the maintainability of it is better than with the NNI. Yeah, you can get good results with it. All right, now let's take a look at number 3, carrier of carrier VPNs. This is a good one, and I'm sure many of you know carrier of carrier VPNs, not because you ever used them in production, but because you might have taken vendor certifications and you were tortured with the theory of it. So the idea behind this is that you basically extend the transport plane of one network across another already existing network. And on a technical level, how this works is it's essentially a layer 3 VPN, but with MPLS labels. So this means that this instance is completely separated from the carrying network and allows that even loopbacks, for example, can overlap. So this is also another tool that you can use if you want to bring two networks together, or if you want to just share the transport infrastructure of the other network with the one network you're trying to get in there. So now we've looked at 3 approaches that get you relatively quick results. But our experience has shown that these 3 approaches that we've just shown you tend to be more like a quick fix. You get rapid value. However, in the long run, they only really get you halfway there, to be honest. So if you implement something like inter-provider setups or NNIs, the distinct IP-MPLS networks will continue to be distinct, and the networks will continue to live on their own administrative islands with a somewhat reliable, regular ferry service in between them. And also, from a social aspect, the teams also tend not to really merge because they're busy doing things on their own islands and maintaining them. So what we've seen is that the real value add, and again, this really depends on what you want or need for your network, you can only get if you build permanent structures between them. So in the form of bridges, for example. And what we've seen is that only through this method you can get to a truly merged network. But again, this really depends on what you want and what you need for a network. If you want to keep them separated on different islands, that's also fine. Okay, so how can you build this bridge? So if you want to build a bridge, you need a blueprint, so you need a plan how to do it, and you need a toolbox. And this toolbox, in our case, is full of different protocols. IGP independent label distribution, like BGP labeled unicast, IGP specific label distribution, like LDP, RSVP-TE, or segment routing, traffic engineering mechanisms, IGP design approaches, and even static routing. So that is basically what we see as the starting point or the general gear that you need to build the bridge. So I mentioned seamless MPLS. Seamless MPLS is nothing new. It's been around for quite some time. There's an IETF draft on it, and it's important to understand that it's not a specific protocol. It's rather a collection of design ideas that make it possible to interconnect different domains or sections of your network, while still maintaining, and that's the important part, end-to-end IP MPLS connectivity. So you can subdivide your network into certain sections, interconnect them, and hence enable a scalability or a possibility to scale to 100,000 to hundred thousands of nodes, essentially. And one of the key elements that you have with seamless MPLS is the clear separation of transport and service planes, so that you do not intertwine them, and make sure that the signaling happens separately, and that you can pull them to different locations and have different protocols signaling the services and the transport plane. And seamless MPLS does that by using a toolbox of already existing protocols, the ones that we've seen on the previous slide, to achieve the architectures that you want. So let's look at a small example, which I named Challenge 1. So what you can see here is a pretty tiny example of a 3-layer design for a service provider network with a core layer. We have an aggregation layer and some edges in the access layer of the network. And I've marked them. So in the core, you usually have very high-scale devices. On the aggregation layer, you have medium to high scale, and in the red area, you have low-scale devices. And the reason why you have this structure is because service providers have started to push out IP MPLS towards the access edges of the network. And the reason they do this is because they want to achieve carrier-grade redundancy for their MZANs or OLTs, so the access equipment. And, well, you can also use spanning tree if you like, but most of the ISPs would, for reasons, rely on routing redundancies, so that's the reason why you often see these setups. So in many cases, what they use in these positions are low-scale merchant silicon devices, for the reason being that they're relatively inexpensive compared to the cost that you would have to pay for a full-scale router. And if you have a large amount of them, that makes absolutely sense to put them there. And sometimes, just to mention it, with some vendors, you can also place MZANs or OLTs that have these functionality built in. But in any case, what they have, or what these solutions have in common, is that their scale is usually extremely limited, along with the feature sets that you can use on these devices. So where does this lead us? Often in these designs, you will find a flat IGP topology. So you will just put all the devices in one IGP, and use a label distribution protocol, which is usually fine depending on the scale. So there's simply no need to divide your network. And well, this is still completely fine until you try to merge it with another network. So let's say you have ISPB joining with 1,000 nodes, and then, well, what happens is the high-scale devices will be fine, the medium-scale devices will be fine, but your low-scale device will blow up in flames, and you will get error messages like this, which you do not want to see in production. So how do we solve this? Well, one approach is to just buy a bigger router. The other approach would be to change your design so that you can accommodate for the increased scale. And the concept or the idea behind this is not new. It's been around for quite some time. So the scenario that I've just shown can be addressed by separating the low-scale devices from the rest of the network, essentially. And you can do so by either using level or area concepts of IGPs, so that you have different sections or domains of your IGP where you operate, and then use something which is often called route summarization. So instead of sharing all the loopbacks and all the transfer networks from the entire IGP, you just send an aggregate route. And this way, the access edge devices that you can see here will not be part of the big IGP domain, and they will not receive all the prefixes, and hence the RIP and FIP scale is drastically reduced. So this is cool. It works pretty well for unicast, for unlabeled unicast, but with MPLS, this is kind of an issue, because route summarization and MPLS LSPs are not really best friends, because usually label distribution protocols, for example, like LDP, they rely on exact match /32 and /128. So out of the box, they will not work with this approach. So there's also a solution for this. And there's essentially two main approaches that we see in this area, which the first one being BGP labeled unicast. And you can see that this is the first tool in our toolbox, the wrench. And BGP labeled unicast is not all that different from normal BGP unicast, with the only difference that it allows you to distribute transport labels. And it does so by allowing you to include a label alongside the prefix and the next hop that you advertise in BGP. And the way that it works is, in this example, that we, for example, have an access edge device in a OSPF and LDP IGP domain, and then we have a kind of border device that is part of both the OSPF IGP domain and the ISS domain, and it will distribute its own loopback in the OSPF domain. And then the BGP labeled unicast route that this border or edge device advertises towards the low-scale device will then contain the next hop of that device that sits in between the two IGP domains. So this way, the downstream router can then install a transport path that is based upon the next hop from that device that sits between the two IGPs. And more importantly, you will only have, in this example, only have one next hop for all BGP labeled unicast routes that you receive. So this 13131313 prefix will be used for all of the routes that this guy over there sends. So you no longer need a full IGP redistribution. You can rely on the route summarization. And the most important part is you can easily filter BGP routes that you receive. That is a main property, or one of the properties that you have with BGP as a distance vector routing protocol, which is not that easy to achieve with a link state protocol like OSPF or ISS, for example. So you can easily reduce the RIP and FIP load. Optionally, just to mention it, you can also build these setups completely IGP-less. So if you just want BGP labeled unicast without any IGP underlay, so to speak, that is also possible. All right, so let's look at option number 2 for this. And that's the good old reliable hammer, LDP. And I'm sure many of you know how LDP works. And maybe not all of you know how the default mode is called. I also didn't know that when I started working on it. It's called downstream unsolicited. And it really describes the way that LDP works, because the way that it works is actually pretty dumb, because it will just dump the entire LDP database towards the downstream device once you establish a session. So then what is even dumber on the downstream device is that by default it will install all of these FACs, these forwarding equivalent classes, on the downstream device. So that is an issue when it comes to controlling the scale of your end device. Because of this, there is another mode to LDP which is not that widely known. It's called LDP DOD. It has nothing to do with the Department of Defense, but stands for downstream on demand. And the idea is that you have to explicitly send a label request, and then only when you've done that, get a response with a label mapping. So that allows you to control the influx of transport label information that you get on the device. And this way, you can easily control the amount of prefixes and transport labels that you install on your box. So if you want to use this with route summarization, you also need to make sure that your LDP implementation supports the longest match extension, so that this requirement of matching on an exact match /32 or 128 no longer exists, and that it can match on a default route. And some vendors also offer you to automatically request the FACs that they need in LDP, so that you don't have to build up a list manually. And also here, if you don't want an IGP, you can also build this completely IGP-less with static routing if required. All right, so what we've now discussed is how to make sure that your network scales, and that nothing bad happens when you join two networks, the IGP domain grows, you have more and more devices in there, and you've put mechanisms in place that make sure that low-scale devices are not impacted by this. And what we've seen in projects where we work with customers is that in many cases for them it turned out to be desirable to actually merge their IGPs. And there's a number of reasons for this. So many times they found out that they want a unification of some kind of inner core network, so that all the transport paths that you have in the network can be used by both ISPs. And another reason that we often heard was that, well, simply it's easier to maintain if you merge the IGPs at some point, because, well, one network is easier to maintain than two networks. Another argument that often came up is that you can have a slimmer protocol stack if you just merge the IGPs. If you have a complicated interprovider option C setup, there's lots of mechanisms in place, lots of protocols. And you also, and that's the last point, need support for BGP labeled unicast across the devices that need to go over the bridge that you've built, the temporary ferry service that you built. Yeah, as mentioned, as a prerequisite, you should implement some kind of mechanisms or make sure that your devices can scale. And one important thing to point out is that you can also do the IGP merge even if your autonomous systems have not been unified yet. And the reason that you can do this, or the idea behind this, is one of the key aspects of seamless MPLS, that the service and the transport planes are separated. So, how do we do this? How do we merge an IGP? So, it comes with a lot of challenges. The first one being renumbering. So, in the projects that we've seen, we really started to think that the engineers out there who make the decisions or the IP address assignments should really start playing the lottery, because there's lots of prefixes that you can pick from, lots of private ranges, but you somehow still end up with some overlap for loopbacks or transfer networks in some parts. So almost in any of the cases, we would have to do some kind of renumbering, which is a bit of annoying because it requires a lot of maintenance windows, and you need to change the transfer networks, loopbacks, and etc. Also, if you have segment routing set up, node sits also need to be unique, because a duplicate node sit is no fun. Other aspects are harmonizing metric values, for example, to make sure that the best path selection in your IGP is based upon the same ideas or metrics that you've assigned, and also other IGP-specific settings like timers, loop-free alternates, etc., so that you have one unified experience at the end of the day for all of the participants in the network. And of course, in case you have different IGPs, like the one uses OSPF, the other one ISIS, you have the additional task of transitioning to a new IGP. That also could come in as a challenge. And just to mention it here, usually this is a great opportunity to implement segment routing. And in the projects that we have done, we have actually done that, and we've had discussions with our customers whether or not to take this leap, to take this step forward. And the cool thing about segment routing is that it gives you a lot of new features, like flex algo, allowing you to make decisions based on different metrics, for example, latency, and use them alongside already existing metrics, or also TI-LFL or segment routing traffic engineering. And our stance on this is that even if you don't need these features now, it is very likely worth the change, because the demands towards your network can change in a year, or maybe in half a year. And if you are already working on your IGP, it is advisable to take the step or the leap towards segment routing. All right, so now we have talked about how to basically merge-proof your network to make sure that the devices can withstand the increased scale. We talked about how to bring together the IGPs, and I've done such an IGP merger, and I can tell you this was probably the most nerve-wracking maintenance window I ever had, because it's one of these events where everything can go well, and you will spend hours being paranoid trying to find out if there's anything going wrong, and or it can be a catastrophe, completely fail, and you'll have to roll back everything. So because of this, because it's just such a sort of a higher risk event if you do this kind of maintenance window, for one customer that we worked with, they had asked us if we can simulate such a merger. And on a technical level, this should be possible, because we have access to both of the link state databases. So we collected this information basically through traffic captures, and then extracted all the link state PDUs. So they were using ISIS. And we then edited the link state databases, which was a very annoying process because all you can see is a hex dump at the end of the day, to insert some more bits that you would have a link between the two link state databases, so essentially merging them, so that there's an interconnect that's not actually there, but we put it in there artificially. And then the challenge was to play out this manipulated link state, this combined link state database back to a DOT, which we've done using a modified or hacked version of BioRD. I'm not a software engineer, so we did it the worst way possible. We just dumped in the array into the code directly, compiled the whole thing, and then shot against our DOT, and it worked. And we were able to show to the customer, or demonstrate to the customer, that the DOT would work, that it would work correctly, that we could see all the prefixes, the transfer networks, the loopbacks in the routing table, and that there were no error messages generated. And then they were happy with it. And the end of the story is that well, the IGP merger was successful. So you might ask yourself, well, you probably have access to an Ixia or a Spirent tester. Why didn't you do that? Just to quickly cover that. It is possible to do it on Ixia, but the issue is that they require a specific data format. So if we wanted to do this, if we had wanted to do this, we would have to convert all the data back into the specific data format and then play it out. It was simply easier for us to hack an existing ISIS implementation to achieve that. All right, that brings me to the end of my talk, and well, now it's up to you. So we've heard about the blueprint, that being seamless MPLS, and told you about the different tools that are there. And what I wanted to point out again, to sum up my talk, is that at the end of the day, when you're faced with the challenge of merging two networks, you need to make the decision. You need to decide what is right for your network. If you like the NNI approach and it works for your network, that is absolutely fine. If you want to merge the IGPs, that is also fine. And if you like an inter-provider setup of some sort, that is also fine. Yeah, at the end of the day, your team and your network just needs to be happy and content with the solution. All right, thank you.
Thank you. Okay. We do have time for questions. Please wave there.
Tom from DKIX. You said, hey, we can have OSPF and ISSS in the same network as well. Mm-hmm. I would assume it would be double trouble, because now you have to know people doing OSPF, you need to know ISIS, you need to redistribute. What's your experience with that? Because I would assume it would be problematic to do that.
Yes, of course. I mean, if you have OSPF in some access areas of your network and then you have ISS in the core, that is more of a challenge, right? Because you need to understand both of the IGPs. But as mentioned, you can also choose a different approach where you use area or level concepts to subdivide the network. So that could be one way to address it. But yeah, at the end of the day, I totally agree. This introduces added complexity, but so do many of the other mechanisms that we've presented. So yeah, well, you need to, it's a trade-off at the end of the day. Yeah.
Falk Burkhoff again. When we plan to harmonize the IGP protocol and changing the one side from OSPF to ISIS, to match both sides having ISIS at the end, can this be done in parallel to the OSPF protocol without harming the one the other, or will there some pitfalls or something like this?
Yeah, I can see Oliver over there laughing, because they've actually done exactly that. So what you can do is you can have this operate side by side, and many vendors have a concept that is called administrative distance or protocol preference. So you can set a preference on which kind of protocol should be preferred over the other when it comes to installing in the RIB. So for a temporary setup, yes, you can absolutely run them in parallel to ease a transition to a new IGP. Yeah.
Okay, I don't see any raised hands anymore, and we are also perfectly on time. Thank you very much.
Thank you.